All right, guys, we are looking at section 3.2, conditional probability in the multiplication rule. This is our day one. We're going to get through examples 1, 2, and 3. So we're going to talk about conditional probability. It's the probability of an event occurring given that another one has already occurred. This right here, probability of B with the long vertical line, A is read as probability of B given A. So in example 1, 2 cards are selected in sequence from a standard deck of 52 playing cards. Find the probability that the second card is a queen given the first card is a king. So we're not finding the probability, like, it's weird. We're only looking at the second event, but we have to take, or the second drawing, I should say. But we also have to take into account the first drawing. So probability that we draw a queen given that we have already drawn a king, okay? Assume that the king is not replaced. This is important because if we don't replace, so like what we're doing is we're assuming that on the first pick, we have drawn a king. We are not putting that card back in the pile. So that means on our second pick, instead of 52 cards, we have 51 cards. Now, because we assumed that our first card was a king, that means that there are 4 queens left in the deck to draw. So the probability that on our second pick, we're going to get a queen if we assumed we drew a king the first time is 0.078. Okay. Conditional probability shows up a lot in tables a lot of the time. So the table shows the results of a survey in which 2,226 social media users were asked whether they have ever been offended by something, meaning posts, comments, or photos they saw on social media. So the total number of people is 2,276, sorry. Find the probability that a user is male given that the user was offended by something on social media. So we are now asking for the probability of male given offended. Whoops, sorry. That should be a parentheses, okay? So what you kind of do when you have a table, it's kind of nice, actually. What you're going to do is you're going to go and you're going to look at, all right, here is the male row, right? We've got male, female in total. And then here is the yes, they were offended column, okay? And so what ends up happening is your numerator is going to be where they intersect, that 532, okay? And then your denominator is always, it's really kind of neat. Your denominator is literally just always the number in that column. So it's 1151, sorry, not 52. So that probability is 0.462, okay? And then we've got to do the same thing. I'm going to have to erase my drawings or my scribbles on my table because I need to use it again for the next one. Okay, so I'm going to scroll up just a bit, guys. So when we're looking at this using the same table, find the probability that a user is female given the user was not offended by something on social media. So when we're doing this, we are assuming probability of female given not offended. Okay, so again, we're going to look at female right here. There's the female row. And then we're looking at not offended. So we're looking at this column. So the number of females who were not offended is 549. And you put that over your total number of people not offended. So that's over 1125. So when we look at that, okay, and we do 549 divided by 1125, we get 0.488 for our probability, okay? All right. 2 events are independent when the occurrence of one of the events does not affect the probability of the occurrence of the other event. So basically it means that the probability of B given A is exactly the probability. So like the probability of me wearing a pair of tennis shoes given that you guys are wearing sandals it's the same. Like I'm going to wear my tennis shoes whether you guys are wearing sandals or not. Okay? That's what that kind of means. It just means that it's not going to be affected. Okay, so determine whether the events are independent or dependent. Selecting a king, where we got? From a standard deck of 52 playing cards, not replacing it. That's your key right there. We are not replacing it. And then selecting a queen. So event A is the first selection, event B is the second selection. We did not replace it. So our second selection of cards, well, no, selection of one card would be dependent on the first one. Okay. Dependent. Did I spell that right? Sure, looks good. Okay. Tossing a coin that lands heads up and then rolling six-sided die and getting a 6. Literally the two have nothing to do with each other, so they are independent. It doesn't matter whatever I get on the coin is not going to affect whatever I get on the die, and vice versa. Driving over 85 miles per hour and then getting into a car accident. Yeah, sorry, that's dependent, guys. Don't speed, drive safe. Okay. Tossing a coin and landing heads up, and then tossing the coin and again landing tails up the second time around. Your individual coin tosses are independent of each other. One does not affect the other. Okay. All right, so what do we got next? The multiplication rule. The probability that two events A and B will occur in sequence. So this is going to be different than like our first couple examples where I just was looking at one specific event. Okay. Probability of A and B, we do the probability of A times the probability of B given A. Okay. And if they're independent, then it's just a nice simple woohoo. We can just probability of A times probability of B. So basically, in words, find the probability that the first event occurs. Find the probability that the second event occurs, assuming that the first one already has, and then multiply the two probabilities. Now, sometimes the first one occurring will affect the second one, and sometimes it won't. But either way, if you find the two individual probabilities and multiply them, you should be good to go. All right, what do we got? 2 cards are selected without replacement. Without replacement means I do not put them back from a standard deck of 52 cards. Find the probability of selecting a king and then selecting a queen. So probability of king and queen, right? Oop, I just did a theta. Sorry, that's a Q. All right, so what we have is we have 4 kings out of 52 cards, right? Times we assume that we drew a king the first time. So we still have 4 queens left, but we did not replace that king. So we only have 51 cards left. And so whatever this is, it reduces down to like 4 over 663, I think is what it reduces down to. Okay. So this is 4 over 663, I think that's right. But really what you want to know is the decimal. So 0.006. Okay. All right. A coin is tossed and a die is rolled. Find the probability of tossing a head and then rolling a 6. These are independent events. Doesn't matter. So probability of tossing head side up and then rolling a 6, okay, is going to be, well, 1 out of 2, because it's either heads or tails. Oh, you know what? I guess I should have done that. Here, let me go back up here. This, if we look at this, would be probability of king times the probability of queen given king. All right, and this is just plain old probability of heads times the probability of a 6. And so then we assume we're on a 6-sided die, so it's 1 out of 6 there. Okay, so that's 1/12, and that is 0.083. Okay. Probability that a salmon swims successfully through a dam is 0.85. Find the probability that 2 salmon swim successfully through the dam. Okay, so probability of successful salmon and successful salmon. Okay, these guys are independent. It doesn't matter. If salmon A makes it through, it's not going to affect salmon B. It's not going to affect salmon C. It's not going to affect salmon D. Like, they're all independent. They're all working on their own. They're not helping each other out. It's just survival of the fittest there. So it's really just going to be probability of a successful salmon times the probability of successful salmon. So that's 0.85 times 0.85, which is 0.7225. And then the last one, 2 cards. And guys, I'm sorry, I gotta move this up a little bit. Okay. 2 cards are selected from a standard deck of 52 playing cards without replacement. Find the probability that they are both hearts. So, probability of heart and heart. Again, because of this whole without replacement thing, these guys are going to be dependent upon each other, so we have to actually look at this. So this is going to be probability of a heart times the probability of a heart, given that I already pulled a heart. Okay? So here's the thing. We got 13 hearts out of 52 cards, sorry. Times, all right, we are now going to assume that our first card was indeed a heart. So that means that there are only 12 hearts left out of 51 cards because I did not replace it. And when we multiply this out, we get a 1 over 17, which is a 0.0588.